Today we're going to have a look at acids and bases, and typically we start mentioning the Brønsted-Lowry acids, and let's give you a little bit about the history of those because it puts things in sort of perspective. So starting off with some acids, I suppose we're back in the sort of 1770s, and we're looking at people like Joseph Priestley. And he's looking at things that we're playing around with, and they were starting to sort of think about things that were acids, and they were discovering that basically we got gases given off, and they discovered things like oxygen being given off, and they were starting to sort of discover things were made of other things. By sort of 1778, then we're looking at what was an acid, and a guy called Lavoisier looking at what was an acid. He got it wrong, but you know, he was sort of getting the idea. By about 1815, then Humphrey Davy came up with an idea about some acidic acids like HCl contained no oxygen. They still didn't really have much idea about what was going on. But by 1832, a guy called Justus Liebig of Liebig condenser fame here defined an acid as something that contained hydrogen. And that wasn't a bad guess really for what we're looking at. So next comes along in about the 1880s, and our friend Arrhenius, and he basically proposed that acids in water, they dissociate, and when they dissociate then they form H plus ions, and that's what acids do, and that bases do OH minus ions. Problem of course is if you don't put it in water and you don't have a soluble base, then the system broke down a little bit. So our next two guys on the scene are in about 1929. So we've got two gentlemen coming in here, and we've got Johannes Brønsted and Thomas Lowry. And they came up with this idea for more solvents, and they proposed this idea of a Brønsted-Lowry acid. And then a little bit later we come along with Gilbert Lewis, and Gilbert Lewis came up with a more general theory that describes an acid, and he created what we call a Lewis acid and a Lewis base. These you tend to do at university, and we're going to stop the story there, and we're just going to look at here Brønsted-Lowry acids, which is a shame really, because as my son likes to tell me, a Lewis acid is a Bronsted base, and it causes all sorts of confusions. But basically when you get to university you forget everything you've learnt up to there and you just concentrate on this, whereas we here are going to look at this bit. So we're going to look at this idea that when an acid is added to water, something interesting happens. So for instance, if I take hydrochloric acid and we add that to water, then basically the HCl is going to disassociate itself into our two ions, our H plus ions and our Cl minus. We think of the HCl here as donating an H plus. So this is my Brønsted-Lowry acid, simply because it donates an H plus ion. So there's that one. I suppose we could look at a different acid. Let's look at sulfuric acid, H2SO4, and for sulfuric acid we get H2SO4. Here it dissociates to give me an H plus ion, again aqueous here, plus I've got my HSO4 minus ion. So the H2SO4 has donated an H plus ion, so it again is, because it donates an H plus ion, then we can say this is a Brønsted-Lowry acid. To make life more difficult, my HSO4 can go on to donate another H plus ion. But that then makes it interesting, because this substance can also go the other way and accept an H plus ion, so therefore we can think of this as something being dibasic, and we'll worry about that in a minute. So let's go back and have a look at some simple things about what are acids and what can we do with them and what are they. And let's start with getting some basic rules down. So our basic rules, we can think of, and we come across two things. We come across weak acids and we come across strong acids. And what's the difference between them? Well, let's think of some weak acids, and the ones that immediately come to mind are that I've got vinegar, I come across citric acid, and I come across ascorbic acid, otherwise known as vitamin C. And these are my weak acids. And you've almost certainly come across the strong acids, hydrochloric acid, sulfuric acid, and nitric acid, the so-called bench acids. These are the strong acids. But the difference simply between them, whether it's a weak acid or a strong acid, basically simply depends on the equilibria. So what do we know about acids? So let's come up with some simple facts about acids. Well, we know they turn blue litmus red. They've got a pH which is going to be less than 7. Technically the definition is at 25 degrees Celsius. What else do we know about them? Well, we know that they will react with a base, or if you prefer, an alkali, and they will do this to give us a salt plus water only. Example of that would be HCl plus NaOH, giving me NaCl plus water. They react with a carbonate, and they react with a carbonate to give me a salt plus water plus carbon dioxide. They also react with metals, obviously the metals they react with, to give us a salt plus hydrogen gas. And the metal here has got to be above copper in the reactivity series. So what else do we know? Well, coming in here, HCl is going to give us simply the chlorides as the salt. The sulfuric acid is going to give me the sulfates as a salt, or maybe we can get a hydrogen sulfate. And nitric acid can give us the nitrates. And in these we're looking at a neutralization reaction, that basically we are taking something that is acidic plus something that is basic, and we're getting something that is neutral. So that gives us this idea of what we can choose here. But there's a couple of other things that we know, and one of my favourite tricks is I'll take some citric acid, pH 2, and I can put my finger in there for a few minutes and I don't mind. And the reason is I do it in solid because simply we've got this idea without water basically that was a joke, acidic properties are not shown. So it is our H plus ion that makes something acidic, and if we're neutralizing something, our H plus ion reacts with an OH minus ion to give us water, which is pH 7, which is neutral. So we get our basic ideas of this that we can actually use to sort of try and work on these things. Now we have a few interesting problems. And what makes our few interesting problems? Well, our interesting problem is that I said that, let's suppose we've got HCl and it's in water. It's going to dissociate and it's going to form, as I said, an H plus ion plus a Cl minus ion. But this H plus ion, now what is it? It's basically simply a proton, and protons can't exist by themselves unless they're in sort of a good physics lab and under extreme conditions. They're incredibly small, they've got very high charge density, and so it's better to think of this as HCl in water is simply makes an H3O plus ion plus a Cl minus ion. Now, for convenience, we normally write that as just H plus, but in actual fact we normally mean this H3O plus. A definition of a Brønsted-Lowry acid is that an acid here is simply a proton donor. And similarly, a base is a proton acceptor. So let's think about what's going on here. I've got my HCl. HCl here is mixed with water. Now this is a proton donor, and the water here can be thought of here as a proton acceptor, and this is one of those equilibrium reactions which gives me my H3O plus my Cl minus. Now this here is an H plus donor, and the Cl minus here is a proton acceptor. So in this case HCl is an acid and H2O is in fact a base. Each acid has an associated base called its conjugate base. So we have our conjugate pairs. So here Cl minus is a conjugate base of HCl, and they form an acid base pair called a conjugate pair. Let's look at another one of these examples. Let's take ammonia, NH3, and this is going to react with water. Now here water is going to help form NH4 plus, and we're going to get OH minus. So in this case my H2O is here a proton donor, and the ammonia here is a proton acceptor. And this therefore means that this NH4 ion can donate an H plus ion, so this is an H plus donor, and the OH minus can accept here an H plus, so here it is an H plus acceptor. This means this is a base, this means this is an acid, this means this is an acid, and this means this is a base. Compare that with the other way round, where I had water here as a proton acceptor, which makes it a base. And that's an acid. So we can already see that we've got a little bit of confusion here about how we talk about things.
You've got to have a little bit of style, featuring Sir Michael Horton,
Alexa,
David Jason and...
Stop. Does worry me, that device. So let's go in and perhaps have a look at some more things about pH, and let's look at the pH scale. So here is my pH scale. I've got this out of my little book of my indicator, and here is my pH scale using my universal indicator. And what we're looking for is about pH 7 here as being neutral, gradually here becoming more and more acidic, or here becoming more and more alkaline. So what is this indicator paper, universal indicator paper? Well, in fact it's a range of different indicators, and there are certainly an awful lot of these indicators that we can actually use. And I was sort of, when I started having a look at this, I was absolutely amazed at the number of indicators there were to sort of play around with, and it's just an enormous number, and these work at a whole series of different sort of pHs, and this sort of makes things really sort of, well, quite interesting really. So we've got a whole series of different sort of range of indicators, and this range of indicators is sort of quite interesting. If I have a look at some of these, then you can see as I just scroll down, there are a terrific number of indicators. These are just in alphabetical order, and an indication of the colour that we sort of get on those. Phenolphthalein is one of my favourite. So we've got a whole series of those indicators, and if we mix them together we can get universal indicator. And there are various sort of, I know, recipes, for lack of a better word, for these universal indicator, but typically bromothymol blue, methanol's the solvent, methyl red hydrochloride, phenolphthalein and thymol blue is one sort of recipe for universal indicator. But having investigated it, there are actually quite a few different ones used by different companies, and they produce slightly different sort of colour ranges. But basically, that's what we've got. Now, if you don't like using universal indicator, then instead you can have one of these, and this here is my pH probe, and it's made by a company called Pasco, and this connects to just a sensor. And before I normally want to use this, I need to take this and I need to basically set it up, and I put it into a series of different chemicals which I know the pH of, and once I've got those pHs, then we can calculate what the pH is, normally to sort of a better number of decimal places, I suppose. So we've got this idea of acids. Let's take this through a bit more. I'm popular today. Now, let's have a look at some of these things. What I've got is an idea about pH. Now, what is pH? So let's write down that pH is going to be the negative log to the base 10 here of the hydrogen ion concentration. Okay, so we've got this idea of what is pH. So let's have a look at something and see if we can do a calculation. So let's take, for example, a solution. Let's go for a 0.1 molar solution of hydrochloric acid, and we're asked, can you give me its pH? Okay, so let's see what we know about this. Well, HCl fully disassociates. Right, so if it fully dissociates, then basically what we're going to have is our pH, and we're going to work that out, and that's going to be the negative log to the base 10 of this hydrogen ion concentration. If we've got 0.1 molar, then we're going to have here 0.1, and what we need to do is get out our calculator to do the work for us. So let's do that. So we've got the calculator, and what I want to do is call up log. This is going to be log to the base 10, and I've got my concentration of 0.1. So let's do that, and it comes up with -1. So I've got here minus my log to that, which is -1, which gives me +1, which is our pH. So my pH here has a value of 1. Okay, so we can work out these things. We can also work these out the other way, and to work them out the other way, let's suppose I've got a solution, and I know it's got a pH of, let's say, 4. So what is the concentration of my H plus ions? So I know that 4 equals the negative log to the base 10 of my hydrogen ion concentration. So in fact, minus 4 here is my log to the base 10 of my hydrogen ion concentration. And what we now need to do is I want to do the opposite. I want to find now an anti-log. My anti-logs are on the same button, shift here, and what I want to do is put this number in here of minus 4. And that gives me the answer of 1 over 10,000, or in other words 10 to the minus 4. So hopefully you can see that. If you can't, then what we want to do is simply I suppose I could sort of change that for you by pressing the SD button on the calculator, and you can see it's here 1 times 10 to the minus 4. I didn't do that for you, so there we are. So we can work out various different pHs, and we can work out the hydrogen ion concentrations. Okay, what else can we do with our Brønsted-Lowry acids and bases? Well, let's see. Just having a quick tidy up around here so I've got room to maneuver, and then we can get on and try and do this. Right, so what have we stated with Brønsted-Lowry acids already? We know that we've got here for my Brønsted-Lowry acid, I'm just going to cheat here, that it is basically a proton donor. And if I've got my Brønsted-Lowry base, then we've got here this as a proton acceptor. We've also decided we've got these conjugate bases. So we looked at HCl going to give me here, I'd have to have it with water really, my H3O plus my Cl minus. So this here is my, if you like, we'll call it base 1, and that goes with my acid 1, and then my water here, this is a proton donor, so this here is my acid 2, and this is my base 2. Nearly got that in. And these are my conjugate pairs. This H3O plus is the hydronium ion. Now we've got certain acids that behave differently. So let's deal with these, and we'll have three terms really. Let's have a monobasic acid, and an example of that would be hydrochloric acid, because that's just going to form one H plus. But we can have a dibasic acid. This is H2SO4, and what this is going to do, it's going to form H plus plus my HSO4, and then we can also make another one of those plus my SO4. So we can do it once and we can do it twice. Not to be outdone, of course, we can go to a tribasic, something like boric acid, H3BO3, phosphoric acid, and this is going to produce first of all my H plus plus my H2BO3. Then we're going to get another one, and then we're finally going to get our third. So we can have monobasic, dibasic, tribasic acids. The most common one is using this H2SO4 because it's got two hydrogen atoms, therefore it's going to be dibasic. Phosphoric acid, I suppose, is another common acid where I come with H3PO4, that we can actually do that. Right, so let's ask now the question, what is the role of the H plus in the reactions? So what is here the role? So let's take an acid plus a metal, and that's going to give me a salt plus water. I need to balance that, so I'm going to have here two of those. Right, now let's think of this as ions. So I've got here two H plus ions, I've got two Cl minus ions, plus I've got my magnesium, which is a solid, and that gives me magnesium 2 plus, which is now aqueous, plus my two Cl minus ions, which are now also aqueous. I didn't write that in. And also I've got here, whoops, hydrogen gas given off, just H2. That was me being a little bit stupid. That and that not doing anything. These are what we call spectator ions. So let's ignore them. And therefore my ionic equation here is I've got two H pluses, which are aqueous, plus my magnesium solid, goes to give me my magnesium 2 plus, aqueous, plus hydrogen gas. So we can see that if we just ignore my chloride ions, then we can see what the role of the H plus is here. The spectator ions don't change during the reaction. Here they're simply cancelled out, and you know that any acid that reacts with magnesium is forming this Mg2 plus ions, so there we've got our simple role. How about if we have something like a carbonate? What's going to happen with a carbonate? Well, we know from what we've done before that an acid plus a carbonate simply gives me a salt plus water plus carbon dioxide. Let's sort of get some idea about what this is doing. So if I have something like a carbonate, let's have copper carbonate, going to react with an acid. Doesn't really matter what acid it's going to be. So I can have HCl here. Then what we're left with when we take out all the spectator ions is we get 2H pluses plus my copper carbonate. Here is going to give me my copper 2 plus ions plus my water plus my CO2. In an aqueous solution, and if I took something like sodium carbonate and I dissolved it, then we'd have my H plus ions. I wouldn't need to have my sodium ions because they're already dissolved, so I would just meet my carbonate ion, and that's going to give me simply my water plus my carbon dioxide. I suppose I ought to put my state signs in. So we can see what's going on here. So we've met the ionic reactions, we've met converting pHs to simply work out its pH, and that is true of strong acids. Now, what happens when we dilute an acid? So let's have a look at here some pH change on dilution. So let's imagine we've got some pHs. Let's have a look at a pH. We've got a pH of 1, and a pH of 1 here is going to give us a concentration, 0.1 moles of H plus ions. Now, if I've got a pH of 2, then I've got simply here a tenth of that. And if we go to a pH of 3, so you can see that when by the time we get down to pH 7, we've got quite a lot of extra numbers in there. How about if we've got something here we want to try and work out? So let's be easy. Let's take 0.1 molar HCl, okay, and let's take just 50 centimetre cubed of that, and we'll dilute that down to 100 cm cubed. And we want to find out what's gone on. Well, on diluting to 100 centimetre cubed, the concentration has been halved from 0.1 down to 0.05 molar HCl. Okay, so now what I've got to do is work out what we've got. So we've got our before, we've got 0.1, and we've done that one calculation before, and that gave me a pH of 1. Now what we're going to do is we're going to try the next one. So let's do the after, and here the after concentration is going to be 0.05 molar, so we can work out our pH, and our pH is simply going to be the negative log of 0.05. So let's throw that into the calculator, and all I want to do is the log to the base 10. I can change this sign back to a minus when I've finished. 0.05, and that gives me minus 1.301, and so minus 1.301 is going to give me here a pH of 1.3. So halving the concentration here doesn't halve the pH. It doesn't even double it, is another way of looking at it. It's going to go because of this log function. So it gives us an idea about acids, that we can play around with these acids to work out what happens. So a way of thinking about this is that with a strong acid, I've got a little balance perhaps here, and we'll have our conjugate acid on this side, and this heavily goes that way to my conjugate base. So if we have a strong acid, what this means, we're going to have a very weak conjugate base. Whereas if we draw this the other way, and here we've got our conjugate acid, and our base here, we can say that a weak acid will have a strong conjugate base. You've got to take care when you use the terms strong acid, weak acid, dilute acid, concentrated acid. A strong and a weak acids refer to their ability to dissociate in water. Strong acids are really good, effective donors of H+ ions in water molecules. And in that case they're mostly dissociated. But if you've got a very dilute solution of a strong acid, the strong acid's still going to be almost completely dissociated. But because it's weak, there won't be many H+ ions, so there'll be a low concentration of the H plus ions. So we have to be careful when we use the terms strong acid, weak acid, and compare that with something that is a dilute acid and a concentrated acid. And we also have to remember that these work well only in normally water. And so you can get an interesting situation where you get a very concentrated acid because there's so little water there. It may actually not be quite as strong as you believe it could be. How do we get with strong acids? Well, I was careful when I tried to choose something. What happens if I take 1 molar HCl? What I did, I took, when I did my example, and I cheated really, I took here, I did 0.1 molar HCl, and we came up with a pH here of 1. What happens if we have 1 molar HCl? Well, that's going to give us, for our pH, it's going to give me the negative log to the base 10 of 1. Let's do that. For mathematicians, this is really quite easy, but for other students, this is sort of a new idea. And here I can shove in my equation and I get 0. I get a pH here of 0. Could it get worse? Well, yes. What happened if I had 10 molar HCl? This is concentrated hydrochloric acid. Normally hydrochloric acid comes as roundabout, I think it's about 36 molar. I think it's something like that. I'm looking for some bright ideas. 5, 10, about 10 molar. Let's say we're going to go 10 molar anyway. If we go 10 molar, this is minus the log to the base 10 of 10. Let's go and calculate it. And I'm simply going to edit this line because it's going to be an awful lot easier for me. And here we get a pH here of 1, but we've forgotten we need to put the negative in there. So this gives me a pH of -1. And that is about as strong as I know that you're actually going to go with an acid. And that sort of worries people when they start to have a look at acids. So normally we don't mention that. So there's some work on acids. This brings us nicely to dissociation constants, where I suppose we ought to start next time. Thank you for watching. I hope you found it interesting learning about Brønsted-Lowry acids and pH, and if it's useful to you, please subscribe and give us a thumbs up, and I'll see you next time on A-Level Chemistry, topic by topic. Until then, stay safe. Bye bye.